Okay, let's start with a joke. How many C++ programmers does it take to change a light bulb? None. A light bulb object would have inherited a change function from a generic light class, so it could change itself. Object-oriented programming really is a different way of thinking. Congratulations on getting this far. As a sort of reward, now we're going to put what we've been learning to use in designing a game engine. I want to walk you through a development process for an entire object-oriented program. Encapsulation, hierarchical inheritance, polymorphism using virtual classes. It's all going to come together as we design a game engine class that can be used for more than one game. So, let's get started. We want to create a system that lets us play two-person board games on a computer. Now, earlier in this course, we showed how we could develop a Connect 4 game. Well, here we want to build on our top-down design from Lecture 15, but now use object-oriented principles. In fact, we'll do this in a class that can handle all sorts of two-person games, not just Connect 4, but games like checkers or chess or Othello. For this implementation, we'll focus on two different games, Connect 4 and Othello, which is known more generally as Reversi. The way Reversi works is that players take turns placing either black or white pieces on an 8x8 board. The game starts with 2 white and 2 black pieces already placed in the middle 4 squares. So let's say that a black piece is placed. It has to be placed next to some white piece, whether beside, above, below, or diagonal. If the new black piece causes any white pieces to be newly bracketed by a pair of black pieces in a row, column, or diagonal, then that causes all of those newly bracketed pieces to switch color to black. And the winner is the one with the most of their color piece on the board after the board is filled up. So, if we want to develop a system to let us play both Connect 4 and Reversi, how should we approach it? Now, as is the case with any approach to software development, the first thing we should do when faced with a programming problem is to stop and think. For object-oriented design, our first thought should be to consider what the objects of interest are. From there, we can figure out what classes we need for those objects. So, let's think about what things we'll need to have in a very general sense. Brainstorming, we'll probably need some sort of class for a game in general, to keep track of whose turn it is and so on. And we'll probably need some game board class to hold the current state of the board. And some way to describe what a move will be, where the one thing that all of our games will have in common is that we have 2 players taking turns. Now those are all kind of abstract ideas, and so they're likely to end up as abstract classes. And we'll also need some more concrete versions of those same classes. The specific game boards for Connect 4 and for Reversi, and the specific moves for Connect 4 and Reversi. So those sound like subclasses. So, if we're to create a Connect 4 board object, that'll be a particular Connect 4 board at some point in time in some game. Now, once we've thought about the classes, the next thing we can do is to start to look for hierarchies. In this case, there are a couple of obvious relationships. The abstract game board ought to be apparent to the concrete Connect 4 game board and Reversi game board. And likewise, the abstract game move ought to be apparent to a Connect 4 move and a Reversi move. Now once we have a general idea of the hierarchy, we need to think about exactly which member variables and member functions each class should have, as well as which ones should be public, protected, and private. For our abstract classes, we'll need to think about virtual functions. For example, the abstract game board doesn't necessarily have a fixed size or layout or anything, since different games will use different game boards. But regardless of the game we're playing, we'll need to be able to display the board so that a user can see it. And we'll need to be able to update the board when we take a move. So we can think that an abstract game board class ought to have some pure virtual functions that will be defined concretely, and perhaps differently, in each of the children classes, such as Connect 4 game board and Reversi game board. To keep track of what we're doing, I'm going to introduce a little diagramming notation here that comes from UML, which is short for Unified Modeling Language. UML is a notation system developed by object-oriented programmers for creating blueprints in the software industry. To give you a taste of how it's helpful, I'll use UML diagrams to lay out some of our classes. In UML, when we describe a class, we use a rectangle with the class name in a box at the top, followed by two other boxes, one giving the member variables, or attributes, and the box at the bottom giving the member functions, also called methods or operations. For designating whether elements of a class are public, private, or protected, there are commonly used abbreviations. A plus sign in front means public. A minus sign in front means private. And the pound sign, or number sign, or hashtag symbol means protected. Italics are used for classes that are abstract and for virtual functions. Now, let me mention something important, really important. To help you out if you rewatch this lecture, I'm going to be including some code as we develop the UML diagrams. But on your own, you should always do your design, creating the UML documents, before you write any code. You should not be trying to write code at the same time that you're making your overall design. Remember, design before you build. So, let's start at the top and think about our game class. A game overall needs to keep track of a few things. First, it needs to have a game board, which is another one of our classes, to keep track of the current state of the board. So we'll call this board. Now, should it be private or public? Well, the game board is not something that we want things outside the game messing with directly. We want to make sure that only valid moves are made, and that players don't make 2 moves in a row, and so on. Since we want to moderate any actions that a program that's running a game can take, this should be a private variable of the game class, meaning that only the game class can access it directly, and others, whether a player or a computer AI, can only access it through functions that the game class provides. Now, we have some options about how we could store the game board in our game class. A game board is going to be an abstract class, and that means that we'll have to have concrete game board classes like Connect4 game board or ReverseI game board. So, how do we store an abstract game board in the game class? Well, the approach we'll take here is to use a pointer to a game board. Remember, it's okay to have a pointer to the parent type even if the actual object is one of the child types. So, back in our UML diagram, we'll write minus board game board star in the box designated for variables. The minus notes that it's a private member variable. Board is the name of the variable. And the game board star shows that the variable is going to be a pointer to a game board. Now, likewise, we'll need to be able to take moves in the game. And like game board, a game move is going to be an abstract class. So, we'll have a game move star, a pointer that we name turn for keeping track of moves. We'll also need to keep track of which player moves next. So, we'll have a private member variable named playerTurn that's an integer. And perhaps we also want to keep track of how many turns have occurred in the game. And a more complex game might keep other information, such as information about the players, though we'll skip that in our implementation. Notice that for each UML entry, we'll have a corresponding line of code. The UML is not code itself, and the order of terms is a little different. So, board game board star in UML becomes game board star board in code. Turn game move star in UML becomes game move star turn in code, and so on. In UML, we were starting with what's obvious for humans: board, turn, player turn, num turn. But in C++, we're starting with the type, the information that's more important for computers. We also need to consider what functions a game class needs to provide. We'll use our UML diagram to organize this. The functions that we want the class to provide will go in the last box. For each of them, we'll think about the function, what name we want it to have, and then what parameter types it takes in and returns. And finally, we'll consider whether we want the function to be public, private, or protected. We'll need a constructor, and it will take in two parameters, one for the game board and one for the game move. And constructors need to be public. So, in our UML diagram, we'll write plus, indicating that it's public, then game, since it's a constructor, then two parameters in the parentheses, board, which is of type game board, and turn, which is of type game move. The function to check for a winner won't take any parameters, and it'll return an integer, giving an indication of which player, if either, won. And this is a function that we want to call from the game class itself, rather than from outside the class. So we'll make it a protected function. And so, using UML, we would write pound check winner parentheses colon integer. Now, we'll likely also want some other functions for taking a turn or declaring a winner. Those will be protected. And these would all be functions that take no parameters and they don't return anything. So we would write pound function name parentheses for each one of them. And finally, we'll want a public function that actually starts the game going and keeps it going until the game's over. We'll call that start game, and thus we'll write plus start game parentheses for it. Let's look at another class, the game move class. Remember that this will be an abstract class. A move is associated with a player, so our game move class will have a member variable, player. We'll make it a protected variable so that all classes that inherit from it will have access to this variable. And it'll also have a pure virtual function, askMove, that will ask the player for a move. It'll take in one integer parameter, the player whose turn it is to move. Now, because this is a virtual function, the UML convention is to write it in italics. We also have our two derived classes, connect4move and reverseIMove. And these inherit from the gameMove class, so we designate that by using arrows with an open triangular arrowhead. The unfilled triangular arrowhead is used to designate inheritance. Each specific move is a little different. A connect4move will need to store a column, the column that a piece will be dropped into. And a reverseIMove will need to store both a row and a column. Each of the derived classes will also need to provide a concrete implementation of the askMove function. Plus, we'll need accessor functions for a move, functions to set a move or that will let some other class find out what the position of the move is and which player made it. And we'll use the names R for row, C for column, and P for player to provide this information. Likewise, we need to define the classes for the game board and its derived classes connect4board and reverseIBoard. Game board will be an abstract class, and it needs to have a few public functions that will be pure virtual functions. It should be able to print a game board, so we'll declare a printBoard function. It should be able to check a board for a winner, returning an integer indicating who won or if it's a tie. And it should be able to make a move, if it receives a move of the appropriate type. All of these functions will vary depending on the particular game, so that abstract game board class can't implement any of them. Now in the connect4board class, we'll need concrete implementations of each of the virtual functions that were declared in the game board class. And we'll also need to store information about the board itself. We'll want to store the number of rows and columns in a game board, since it can potentially vary. We'll use a vector of vectors to store the information at each point in the board. Finally, we'll also have a couple of constructors, one for the default size connect4board, and one for a board where we specify the number of rows and columns specifically. In the reverseIBoard class, just the one default constructor is all we need, since the board will always be 8 by 8 in size. Again, we need to store the board information with a vector of vectors. And we need concrete implementations of the virtual functions declared in the parent class. Okay, at this point, we basically have our entire set of classes designed. Now we might, and in fact will, end up wanting some more functions than just these. Some functions will be too large to do everything in one function. So using top-down design principles, we'll want to divide those larger tasks into smaller ones. For the Connect 4 board, you may remember that we need to check for winners in various directions. So we'll include functions to check for winners in the vertical, horizontal, and both diagonal directions. And we'll also have a check to see if the board is totally full. Now all of this is similar to the procedural top-down design that we did in an earlier lecture. But now these are member functions of the Connect 4 board class. Likewise, for a reverse I board, we're going to want some additional functions to help us change the board. In particular, when we place a piece, we might need to flip pieces in any of 8 directions: up, down, left, right, and along the 4 diagonals. So, we'll create 8 additional functions to help mark the board in those 8 directions after placing a piece. Now, realistically, when you're designing a set of classes, you might not know every function that you need right at the beginning. And that's okay. You might need to change your class design as you build, though hopefully you'll have the major parts of the design in place. So, with our design finished, we'd now want to start coding all of this up. The full coding here is several hundred lines, so we're not going to go through it all line by line. But I'll show you everything that I've coded, and I'll highlight how I've handled some key specific parts of the program. And the full program is also available for download online. A good place to start is with the implementation of our game class, since it's the most fundamental of the classes. Let's compare the class design that we came up with in UML with what those same steps look like in code. We already saw that the member variables would be declared as a game board pointer board, a game move pointer turn, an integer player turn, and an integer num turn. The next thing in our design were the member functions of the class, starting with our constructor. The constructor is going to take as input a game board and a game move. Now, our design didn't specify, should we pass by reference or pass by value? Well, the game board and game move classes are abstract, and they don't have a specific value. So these have to be passed in by reference. So we write gameboard ampersand b to get a reference to the game board, and game move ampersand m to get a reference to the game move. Inside the constructor, we just get a reference to the game board, in other words, a pointer to the game board, and we assign it to the board member variable. And we do the same thing for the game move, assigning it to the turn member variable. That's all we need to do in the constructor. The next function in our design was a checkWinner function, which was protected. We're implementing checkWinner within the gameboard class, since the gameboard itself determines who the winner is. So, our code for checking for a winner just calls the checkWinner function in the gameboard that we've stored. Our next routine to look at is the takeTurn routine, and this should take a turn in the game. Now that means that we want to first have the board printed out to the screen, so we call the printBoardMember function of our board. We then want to get the move that the next player wants. We have a member variable playerTurn that should say whose turn it is, so we pass this as an argument to the askMove function of our turn member variable. And that will call askMove in whatever game move the turn variable is pointing to. Finally, we'll need to update the board based on that move. So we'll call takeTurn on the board, passing in the move that we just got to the game board. Our declareWinner function is several lines of code, but it's really just checking the various possible endgame situations. We determine winners based on the board status, so we just call checkWinner on the board itself to find who the winner is, and we print out the final board and a message about the winner. Our final function is startGame, and this public function is probably the main one inside the game class. It's the function that actually makes the game run. In this function, we initialize our member variables to 0. We then enter a loop that will continue as long as the checkWinner function in the gameboard class reports that the game is not over yet. Within the loop, we first take a turn, calling takeTurn that we defined just above. After that turn is taken, we switch which player's turn it is, we increment the number of turns, and we're done. When the loop finally finishes, that is, when the checkWinner function says that the game is over, then we call our declareWinner routine to print the result. So that's the game class. We just had to implement each of the functions. Okay, now let's turn to the next thing we defined, the abstract base class GameMove, and its concrete derived classes connect4move and reverseIMove. As the UML shows, our base class has just one protected member variable and one pure virtual function, askMove. See if you can implement this GameMove class yourself. There should be just one member variable and one pure virtual function. Well, here's all that class involves. We have our single protected member variable, the integer player. And we also have our pure virtual function. The askMove function takes in an integer parameter, and it doesn't return anything. Therefore, it has a void return type. And because it's a pure virtual function, we write =0 at the end. Now, let's look at one of the two classes derived from the GameMove class, say connect4move. Notice that this is a derived class from GameMove. There's one private member variable, an integer, giving the column into which we're supposed to place a piece. The connect4move provides a definition for the askMove function that was a virtual member of GameMove. This takes in the player number as a parameter, and it uses that to set the protected member variable, player, that was inherited from the GameMove class. It reads in the column number from the user, storing it in the column variable, and adjusting to start numbering at 0 instead of 1. And finally, we have the accessor functions C and P that return the column for the move and the player who made the move. These are again quite straightforward. And that's all there is to the connect4move class. Implementing the reverseIMove is similar. There are some small differences here, highlighting the unique differences between the two games. The reverseIMove needs both a row and a column, so there are two member variables stored, and two pieces of information asked for from the user. But it's clear that both the connect4move and the reverseIMove classes are closely related, and they both implement the necessary functions needed from a GameMove. Our remaining class implementation is the GameBoard class, and as you might expect, this is where everything gets much more involved. So, I'll only point out a few highlights of how these implementations are done. I hope you'll take the time to study the details on your own, or even try implementing some of these parts yourselves. First, our UML diagram gives the design of our classes. Our GameBoard class needs to have 3 member functions. And we saw all of these getting called from back in our game class implementation. The actual concrete classes will implement those functions, as well as provide constructors and member variables to hold the particular board needed for that game. So, implementing the GameBoard class itself is very easy. It's just a matter of declaring a class and creating a few pure virtual functions. Since we're not providing any implementation of those functions in this class, there's nothing more to define. Okay, now let's consider one of the concrete implementations. The connect4 board implements the board for playing connect4. And the basic operations provided here mirror those of the connect4 game that we developed in Lecture 15 earlier in this course. In fact, if you compare the code, you'll see that it's almost identical in many places, with the only differences being that we can use member variables for the board and the number of rows and columns, rather than passing information through parameters. There's one thing that I want to highlight. It's something that's kind of tricky in the way we designed this set of classes. You'll notice that we have a routine takeTurn that has a parameter that's a connect4move pointer. The routine itself is pretty straightforward. It uses the accessor functions that we provided in the connect4move class to get the player who made the move and the column, and then it updates the board appropriately. The thing is, if you remember the definition of our virtual function, we're not supposed to be passing in a connect4move pointer. It's supposed to be a game move pointer. However, a game move on its own doesn't have the specific member functions that we need, like getting a column number. So what we need is a connect4move pointer, and what we have to implement is a game move pointer. So how do we get from the game move pointer to the connect4move pointer? Well, here's a simple solution. We just convert our game move pointer to a connect4move pointer, just like we would do other type conversions. We put the new type in parentheses in front of the previous one. And this will work fine. The compiler just says, oh, this pointer to a game move, I'll now treat as a pointer to a connect4 move. And then everything can be called just like we'd hoped. We could also look at the implementation of the reverse-I board class. Some parts of reverse-I are easier than connect4. For example, finding a winner just means counting how many of each color piece there are once the board is full. Other parts are much more complex. For example, placing a piece on the board requires analyzing the existing pieces and perhaps flipping several to the other color. Now notice that, like the connect4 board case, we have to convert a game move pointer into a reverse-I move pointer to get access to the particular move functions. And also, like the connect4 board, we defined some extra helper functions to keep code to a manageable size, since the process of looking at adjacent pieces to the left and right, up, down, and on all four diagonals is a lot of code to put into one place. So, we created 8 different helper functions, each of which is defined as a private member function. And we can then call those from our take-turn function. Let's look at one of these to get an idea of how they work. The markDiag_UL function will look at the diagonal heading to the upper left, and it'll flip any pieces to the opposite color if those pieces were bracketed appropriately. So this routine takes in the row and column of the piece that was just placed as parameters. First, the routine finds the opposite color from the piece played. Since pieces are numbered either 1 or 2, the opposite color will be 3 minus the piece just played. Next, it'll go through a loop, marching to the upper left as long as pieces are of the opposite color. And it does this with a for loop. Now notice that the loop starts with the square to the upper left of the piece just played. I gets row -1 and j gets column -1. The loop will continue as long as the square is still on the board. That is, as long as I and j are greater than or equal to 0, and the square still contains the opposite color piece. Every iteration of the loop decrements both I and j by 1. Now there's nothing to actually do in the loop. The idea is to just loop until you either leave the board or find a square that's not the opposite color. Now after the loop, we need to check to see if we had pieces bracketed. So we check whether the final square that we ended in was on the board, that is, that I and j were both greater than or equal to 0, and that the square that we ended on has a piece that matched the original piece played. If this is the case, then the pieces were bracketed, and we need to flip all the pieces in the middle. And this is done by looping over those intermediate pieces again. Now there are helper routines that are similar for each of the other 7 directions. The final piece of our program is the main program. We just ask a user which of the 2 games to play. Depending on the game, we declare either a connect4 move and a connect4 board, or a reverse-I move and a reverse-I board. We then create a game, using that board and move as arguments to the constructor. And we start the game by just calling start game on that game. That's all. And with this, we can actually play the game. We first enter the game we want to play, and then the game will proceed, asking player 1 and player 2 for their moves and updating the board appropriately, eventually declaring a winner. Now, if you wanted to, you could create other subclasses for additional games, like checkers, or chess, or Mancala, or whatever. You'd just need to create new classes derived from GameBoard and GameMove. Now, there's a lot more we could do in regards to object-oriented design. It's just like playing a sport. You learn the basics, and after you've been playing a while, you start seeking out the ways that you can really improve your play. So whether it's learning more about UML, learning object-oriented design principles like solid or design patterns, or just plain practicing, there are lots of ways to improve your object-oriented programming skills. In fact, templates and the search for repeatable solutions take us beyond object-oriented programming, into what's often called generic programming. Generic programming helps us describe a concept in a way that's not tied to any specific class or type. It's like polymorphism on steroids. In the next lecture, we'll see that generic programming is also core to the development of one of the most useful libraries in C++, the Standard Template Library, which can save us a ton of time. See you there.